Okay, in this last video, we want to show one more example of proving that two sets are equal. In this case, we're going to take, the theorem says to take three sets, A, B, and C, and show that if you do A union quantity B intersects C, is the same thing as taking the quantity A union B and the quantity A union C and intersecting them. Again, I talked about with De Morgan's laws, there's some kind of algebra between intersections, unions, and complements. Here we're seeing that there's some kind of algebra between, excuse me, between unions and intersection. That if you that you can distribute a union over an intersection um, is basically the way to think about what this is saying, right? And so before we prove it, again, I want to just draw a diagram to make sure that you understand why this could possibly be true. So now I need three sets. So I have A, B, and C. And on this one, I'm going to just show what the left-hand side is. So if I want to just show what A union B intersects C is, then the union means I have all of A, and I have all of B intersects C. So I just have to add this little bit over here. Okay, so when I take A union B intersects C, that's what I'm talking about. And then on the left, I want to just think about what happens if I take A, B, and C and just look at A union B. So then in that case, I get this guy right here. And then I want to draw one more picture to complete this idea. So now I have A, B, and C. And you just want to think about what would happen if I just took A union C. So then I would get this guy. And now we just want to look and at these two pictures on the right and think about what happens if I intersect the blue with the green. And you can see if you intersect the blue with the green, both of them have A completely in the blue and completely in the green. So you get all of A. And the only part that's missing from the intersection is the overlap between B and C, which is not already in A. And that's exactly what you get when you take A union quantity B intersects C. And so we see just in the pictures that this seems to be plausible. And again, though, we want to give a proof now because the pictures are a little bit deceiving. Sometimes we maybe just drew really nice sets, and we want to make sure this is true no matter what the sets A, B, and C are, no matter how crazy they are, right? So we want to show that A union B intersects C is equal to A union B intersect A union C. So first, we will show that A union B intersects C is a subset of A union B intersect A union C. Okay, that's our only strategy, right, for showing two sets are equal. So that's the strategy we're going to use again here. And so to this M, let X be in A union B intersect C. Okay, now in this quantity, we're going to unpack definitions. The first definition to pack is the union, right? That's the outermost operation. So by definition of union of sets, we see that X must be in A. Sorry, I wrote the wrong thing, not and. So it's a union, right? So it's X must be in A or X is in B intersect C. Okay. So now, by definition of intersection of sets, if X is in B intersects C, then notice I say if here because I don't actually know that X is in B intersects C. There's an or here. So I have to say if I'm in the case where X is in B intersects C, then X is in B and X is in C. But this is a conditional statement because of this or. All right. And so just to wrap up what we've shown so far, so we see that X is in A or X is in B and X is in C. All right, now if you think about what that or statement is saying, X is in A or X is both in B and C. All right, so then there's two cases that we need to look at, right? So case one. So that case is if X is in A, then by definition of union, that means that X must be in A union B and X must be in A union C, right? Because in order to be in a union, you have to be in either A or B, but you're in A. So you're in A or B. And in order to be in the union here, you have to be in A or C, but you're in A, right? So that's good. And so then now by definition of intersection, X is in A, oops, A union B intersect A union C. Okay, but that was under case one, right? If you're in A. Now case two. Well, the other case is if X is in B and X is in C, then by definition of union, X is in A union B because it's in B, and X is in A union C because it's in C, right? And then again, by definition of intersection, X is in A union B intersect A union C. Okay, so both case one and case two worked out. Those are the only two cases. So now we just notice that in both cases, X is in A union B intersect A union C, and hence we've shown this the first subset relation that we want. Okay, well that's only half of the proof, right? The other half will be somewhat similar, but a little bit different going the other way. So now we will show that the other way around. So we want to say that A union B intersect A union C is a subset of A union B intersect C. Okay, so to this end, let X be in this A union B, intersect A union C. Okay, then by definition of set subtraction, sorry, not subtraction, set intersection, we find, well, it must be the case that X is in A union B and X is in A union C. Okay. Now, by definition of set union, we find that X is in A or X is in B and X is in A or X is in C. Now, the point here is that in both parentheses, there's a possibility that X is in A. So if X is in A, then both the ands are true, right? So that's going to be one of the cases. And the other case is that if you're in B and you're in C, right? And those are kind of the two cases to look at, because as soon as you're in A, you satisfy this entire requirement. So that gets rid of being in A as a separate thing. And then as soon as you're in B and C, you also satisfy both requirements. So that's what we see from this. So see that either X is in A or X is in B and X is in C. Okay, so now we have two cases, right? So case one, if X is in A, then by definition of set union, we see, well, they were basically automatically done, because now if you're in A, then you must also be in this way more complicated looking set for this case. Because you're in A, and to be in the union, you have to just be in A or this other thing, but you're already in A, right? So that's no problem. So now case two. If X is in B and X is in C, then by definition of set intersection, X is in B intersect C. Okay, but now by definition of set union, we find then that X is in A union B intersect C. Yeah, because if you're in B intersect C, then you're in the union of B intersect C with anything else, basically. It doesn't matter because you're already in B intersect C. Okay, so now in both cases, we see that X is in A union B intersect C. And so we have shown that A intersect B, sorry, I did this backwards. A union B intersect A union C is a subset of A union B intersect C. And since both A union B intersect C is a subset of this guy. Am I writing this backwards? Oh, sorry. A union C and A union B intersect A union C is a subset of this. We see that A union B intersect C is equal to A union B intersect A union C. Okay, again, on the worksheet, I'm going to have you do something similar, but be careful. It's a similar thing, but it's not going to be the same proof. It's going to follow, again, similar lines, but you cannot follow exactly the same steps. So here, now you'll say A intersect B union A intersect C. This is what will be on the worksheet. So what you can do, which is the same, is to write down the definition of everything that's involved and unpack the definitions until you show that something on the left-hand side is in something on the right, and vice versa, right? So you can use that same procedure, use similar reasoning, but it won't be exactly the same. Okay, so the worksheet is due when I get back next week, and feel free to talk to each other to work out some questions you might have, but also feel free to email me and I'll try to get back to you as soon as I can. See you next week.